Hi everybody and welcome to this webinar. I'm Marian and I will be your host for an hour. So today we are going to see an introduction to the DoE module that has been re-engineered in the process of re-engineering the Unscrambler. So now we have the X version. So during this presentation I will first give you an introduction about design of experiment, and then we will see the new functionality of the DoE module in the Unscrambler X. So we will see about the interactive interface and also how we can use it and see the different type of results depending on which type of analysis we are performing. And then I will give you a demo, and at the end of the presentation you can use the chat of GoToMeeting to ask me some questions. So here we are going first to see what is design of experiment. So we have first a definition here of design of experiment. So it is a series of tests in which purposeful changes are made to input factor so that the causes for significant changes in the output responses can be identified. So in this definition there are several things that are very important. So the first one is that DoE is a series of tests. So you need to do a lot of tests. Well, not a lot. You need to do several tests, and you know in advance how many tests you are supposed to perform to get an answer. Then you are going to make some purposeful changes. So which means that it's very structured. The changes you do on the input factor, they are a combination, and it's very precise. So you have to follow what you have to do. And then what you are looking at is to know if on the responses, so on the output responses, you have a change that appear. And if there is a change, you want to know if the change is significant or not, so if it has a real impact or if it's just noise occurring. So that's about the definition. And then if we take it into more practice, we have a lot of variables, and we have what we call the factor that we can use in the design. And then we have other factors like uncontrollable or fixed factors. Those ones, they will not be part of the design, but we know them. And then we have the unknown factors, the one we don't think about that can have an impact on the process, but they do. Like the humidity, for example. You don't think about monitoring the humidity of the factory, but maybe it has an impact on the process. So that's the different factors. And then we have the process. And on this process, we choose to select some responses that are more interesting than others. And the goal of design of experiment is to know if those factors that are in the design have an impact on those responses. So the principle of DoE is basically to perform the least number of experiments to cover the design space, but to do it in an efficient way, so as you know, well, what you want to know. So here we have a design space of two variables, x1 and x2. They are the two factors I can vary. And both of them, they have a lower limit, so here mean, and an upper limit that we call max. So in blue, we have the design space. And then I can just place it randomly. If I want to make 9 experiments, I can just place them randomly. And maybe I get a good answer, but most unlikely. So the best way to do it is to perform experiment in a very structured way to cover the full range and the full design space. So we also do use design of experiment because what we call the scientific approach, which is also called one variable at a time, is limited. So the one variable at a time approach says that in order to establish a relationship between cause and effect, each cause must be investigated separately, all other conditions being fixed. The problem with that, we are going to see it now. So here we have again x1 and x2 that are the two factors I'm going to vary. And let's fix first x2. So I fix x2 to this value, and then I can go along x1. So I can vary x1 first. And I can collect responses. So here is my responses that I'm collecting, and the size of the dot is proportional to the response. So we want to increase the response. So when I vary x1, you see that the best x1 value is this one here. So what I do next is that I fix x1 and then I vary x2. And here I'm quite lucky because I will find that the intersection is really where I find the best result. But if not, if I was finding something best here, I will have to fix again x2 to this value and vary x1 again. So it can take a lot of time, and you never know how many experiments you are going to do in the end. Also, the problem is that you might not find the actual optimum. So here you found a local optimum. So it's this cross here, so the intersection here, as you can see, because we have a contour plot here, will give the best answer. But it's not the real or actual optimum. And this one, you cannot find it this way. So to do that, what you need to do is basically to find a model. So the DoE goals, there are two. The first one, and the most important one, is to find the model terms that are significant. So there are different type of model terms. You have linear, so that's the main effect, and then you have interaction between 2 or 3 variables. After 3 variables, it's a bit too complex and it might not be relevant. So usually you will always have 2 or 3 variables. Then you have the quadratic term, so that's the cubic term, no, the square term. And then you have the cubic terms. So here I wrote an equation. So you have y, which is the response, is equal to a combination of b coefficient. So here we have b0. And then we have other coefficients that are related to different type of factors. So here we have the main effect factor. Here we have the interaction between 2 factors. And here we have some square terms, so quadratic terms. So we can do that for one response, but we can do it on several responses. And then we can make an optimization on multiple responses. So then we just have to solve an equation system. So that's for the DoE goals. So the logical approach when you do DoE is first to set the goal of your experimentation. And when you set the goal of your experimentation, basically you set the model types that you want to investigate. Then you need to select the variables that you want to include in the design, and also the responses that you want to study. And based on that, you will be able to select the appropriate design. So here is an example. We can, for example, maximize the quality of our cookies. And when we say maximize, it means that we want to optimize. So when we want to optimize, we want to know the response surface. So here we need a quadratic model. Then I can decide to have 3 variables that I want to vary in my experimentation. So for example, the cooking time, the temperature, and the chocolate content. And then I can select some responses. So here I took the stability best before date, preference, and cost. And based on that, so because I want an optimization and I have 3 variables I can vary, I will select the design I need. And here in this example, the best suited design will be a central composite design. So for the new module in Unscrambler, we have kind of follow those steps. So we have an interactive interface. So to launch the DoE module, you have 2 access. The first one is from the menu Insert and then Create Design, and then you will start to create a new design. But you can also open the wizard from Tools and then Modify or Extend Design, because a design can be modified or extended. So you get it from the Tools menu. So let's see how it works. So here you have the top of the wizard that shows you different tabs. And basically you navigate it from the left to the right with different tabs where each tab has a specific function. But you can also go back and forth. If you made a mistake, you can go back, make changes, and then go forward again. So let's see how it looks like. So here we have the Start tab. So that's the first tab. The first thing to do is to set a name for the design. So here I set the name test. And then you will have to select your goal. So there is 3 different types of goals. There is screening, when you just want to see and know about the main effect. Then you have screening with interaction. So that the main effects plus interaction. So you can have several types of interaction and with or without confounding pattern. And then optimization, which is for response surface modeling. So when you want to have the square terms or cubic term. Then you have a description field. So here you can enter some information. So here I just typed test of the DoE module. And you can fill it up. And this will be saved. Then we have the history field. So this is created automatically by the computer. And it will take the ID of the person making the DoE. And also giving time and date. So then also here we have some kind of color-coded signal. So you have to have everything green, and then the finish button will you will be able to push it, and then you will get the design. So this is for the Start tab. Then we have define variables. So there you need to define all the variables. So it's very easy. You use this bottom part here, where you have some radio button and some tick box, and also some field that you can edit. So what you do is that you write, for example, here cooking time, and this is a design variable. There is no constraints, and it's a continuous variable. So then you have to set the ranges, so the minimal and maximal value, and you do that for all the 3 design variables. And then we have 2 response variables, so preference and cost. So those one you just tick response here with this radio button. And then you go to the next tab. In the next tab, you have to choose the design. So there is an auto selection that is done by the software. So it will choose a design that is supposed to suit best your needs. So here, as you see, we are in beginner mode, so which means that everything is stated as action, so you can understand what is the action behind which design. If you go to the expert mode, you get the name, the real name of the design. So here we should be doing a fractional factorial design. But maybe you don't want to, so you do a full factorial design, and here you get a warning, because, well, what you decided to do now is not really suited with what you define as a goal and the number of variables that you had and their constraints, if any. So what you can do is that you can say, okay, maybe I can change my goal because maybe I'm interested now in knowing about the interaction as well. And then if you go back to choose the design, as you see, the one that is suggested is in bold, and it's a full factorial design, so you can change to that. If you change again the goal and go to optimization, you will be directed to a central composite design or a box banking design. So, but let's take a fractional factorial design. So here we have a fractional factorial design, and it gives me the confounding pattern that apply and the number of experiments to run. Also the number of samples that is suggested. So depending on your goal, you can select maybe a different type of design. So here, for this example, we only have full factorial design and fractional factorial that are available. Gleichberg-Man being the same, or the inverse of the fractional factorial. So here, nothing much to do. So then we can go to the next tab. In the next tab, that is called additional experiments. You can do 3 things. The first one is that you can replicate the design. So the replication, you deal with it here, and it tells you how many samples you will have to perform in this replication. Here you can add some center samples. So by default there is 3 center samples, and here you can add some reference samples, as many as you want. The next tab is randomization. So here we can organize how we want to have our experiment. So we can randomize everything. So here by default it's randomized. And as you see, all the variables are randomized because there is a yes in the randomized button column. But if I click on detailed randomization, I'm able to change that. So I can untick one of those variables, like temperature, and then when I will re-randomize, I will have the temperature level that are kind of fixed all the time. And the rest is randomized. The next tab is the summary, and it gives you some information about the number of experiments that you can perform. So here with the fractional factorial design in 3 variables, we have 4 cube experiments to do and 3 center samples, which makes 7 experiments. However, here I've been entering some value for the power of the design. So it's very important to calculate the power of your design. So here we have 2 response variables, the preference and cost, and we have to know about their standard deviation. So for example, the preference of the customer on those cookies might be 0.4. And for the cost of production, it can be 0.1. So then we need to know what we will consider to be the least significant difference. So it means what do we really want to see as an effect. So maybe we can say for the preference, if you increase from 0.6, it's already something good. So what we need to do, and we can do the same for the cost. So here I put 0.3. And then I can just click on recalculate power, and it will give me the power of the design for each of those variables. So for preference, I have a power of 0.32. A minimum power is 0.8. So this is not good enough. But for the cost, I already have a good power enough. So to increase the power, you need to have more experiments. Or you need to change the least significant difference, but that is less an option usually. So maybe we can increase the number of experiments. So the first thing that you can do is that from a fractional factorial, you can do a full factorial. So you go back to choose the design, you change to full factorial, and then you go back to summary and you click on recalculate power. So here with 8 experiments, we get a power of 0.56, so it's still not good enough. We need a bit more experiments still. So what we can do is that we can increase the replication. So instead of having only 1 replication, we can do 2, and so we have 16 samples, plus the 3 center samples. So we do those, if we increase that, so we have 2 times 8, 16 experiments. Now we get a power of 0.85, and that's good enough to be able to see a difference of 0.6 as a significant effect. So now that we are good with the power of our design, we can go to the finish table, to the design table tab. And so as you see here, we have the first series of experimentation, then the second series, and then the 3 center sample. Here I'm looking in a standard order. I could also look at it in randomized order. I have actual value here, but I can get the design value. So the design value, basically, they are the matrix that we use to compute the effect. So it's coded in -1 and 1, and 0 for the center samples. So now we have finished to set up the design, so we can just click on Finish. So if I conclude on the design creation, now the workflow makes it much easier to make a design that is good enough. So you have a lot of guidance to find that the best design that you need, and also with the calcul of the power, you are sure that you will be able to find the minimal effect that you want to see. Then we have analysis and extension of a design. So here we have the tables, how they appear in the Unscrambler. So we have 2 tables. We have the test response, and then we have test design. So here is the design table is divided into several types of samples, and also some several types of variables. So here we only have the main effect because it's it was a fractional factorial design with 3 variables and then only 4 experiments. So here we have filled up the response variable, preference and cost. So we can go to the analysis, and in the analysis you have 2 choices. You can either decide to use the classical DoE analysis, which are Sheffe and MLR, so Sheffe for mixture design and MLR for most of the other. And then you also have the option PLS analysis. So then you go to the next tab, which is model input, and you need to, in the predictor, set up the design table, and then in the model you can have different models. So here we have only main effect, but sometimes you may have other design, other model available. So here we only have 3 effects that will be estimated, A, B, and C. If you, when you have been analyzing, maybe you see that the effect C is not important, so you can just take it and move it to not estimated, so then it will recalculate without the parameter C. And at the end you have to set up the responses, so you have here the test response matrix. So now we can see the different results. So we have an effect summary table that shows you the significance of each effect by some type of code and some color as well. So here we have that temperature and chocolate content are both significant for preference and cost, but the cooking time is not significant neither for the preference or the cost. Then we can look at the p-value and also at the effect value. So, well, the greener or the darker the green, the more significant the effect. So the lowest is the p-value. So here we have a very low p-value, which means that this effect is very significant for preference. It has a big effect value. And temperature is a bit less significant, but still very significant and has a smaller effect. And then you can get the same type of result in the ANOVA table, where you can check that the model is valid and then that the different sources of variation are also significant. Then there are some other type of plots that we have. So we added this one, this is called Diagnostic, and where you can see the samples in random order, and you have the actual value, the predicted value, the residual. So here what we can see is that there is a big difference between the actual value and the predicted value for the center sample. So maybe there is a curvature effect. So then we can investigate and look at maybe the effect visualization. So here we have the effect of temperature for the preference, and as you see we have kind of a curvature effect between the low and high levels. So the center level is lower than both the low and high value. Same thing for the cooking time. And we don't see it significant because basically the value at low and high are very similar. So maybe here there is something to do with going a bit further and investigate more, maybe do a response surface analysis. Also because in the order here we haven't randomized the center samples. So maybe there has been a deviation at the end of the process. So maybe because here we have the residual in the experimental order. So at the beginning we have no residual, and then we have a huge residual that goes in the same direction. So maybe there is a bias. So now we can maybe extend this design. So we go to Tools and then Modify, Extend Design. You select the design that you want to modify, and you have a lot of information about it. And then it reloads all the information in the design wizard. So here maybe you just change the goal, you set it as optimization, and when you arrive to design detail, you have selected to do a central composite design or a box band can design. and you have 4 options. So you have to choose between those 4 options. The default one is a circumscribed design because it's the one that works the best for the full design space. But sometimes you have some constraints, so you can select one of the others. Same thing, you just create the design and then you fill up the responses, and then you get a new ANOVA table with a bit more sources of variation because you have to add the interaction factor and the square term. Everything is almost significant. We have only this effect, which is an interaction, that is 0.08 for the p-value, which means it's at 8% it will be recognized as significant, but if we take 5% it is not. So that's how the model is. And then we get a nice response surface and we can try to see where we want to be so we can optimize the preference, and then we can also think about the cost and see a dual optimization. Some other results that are a bit different from the general result are when you are dealing with category variables. So here I made an example with apples. So we have 2 different variables that are category variables. We have the origin, which is France, Spain, and Portugal. And then we have the type, Gala, Golden, and Granny. And we have, again, a response variable that is preference. So what we will do is a full factorial design, and we will not replicate it, so we have 9 experiments to perform. So we can only estimate the main effect. We will not be able to get the interaction factor. So we just run an ANOVA in the same way, and what we get is that the model is significant and both variables are significant. One is more than the other, so the type is more significant than the origin. So here we can see the effect value for each level. So we can see that, well, what makes the apple better in terms of origin is France, and worse might be Spain. And then we have the Gala is having a very big impact, and the Golden is a very negative impact, and Granny is a smaller deviation to the average. So we can also look at another type of result, which is multiple comparison. So here we have 2 results. We have the distance table. So basically that's the difference between the averages at each level. So between Gala and Gala, well, it's 0. And then Golden and Gala, it's 3.76. And here we have the critical distance for this design, it's 356. So here I have a value that is higher than 356, which means that Gala and Golden doesn't have the same type of effect. However, Gala and Granny, the difference is only 2.7. So it means that they have a similar effect according to this critical distance. So they will be in the same group. And Golden and Granny, they only have a difference of 1, which means that they also will be in the same group. So in terms of groups, we have 2 groups. We have Golden and Granny together, and Granny and Gala together. So, but those 2 groups are separated. So yeah, so if you want to increase the quality, the preference of the people, you should definitely take a Gala apple. So now we can look at the result when we analyze the result by PLS ANOVA. So same thing, I will do it on the apples, and so I check here method PLS analysis, and I will look at the main effect of those 2 variables. So what I get is well, PLS result. So here I have the score and loading plots, and I can make some groupings in the plots. So here I have grouped the samples by category. So for the apples, for the type of apple, so we have the 3 Golden that are clustered together, the 3 Granny, and then Gala. And because we have the preference in this direction, we know that Gala will be the one that is preferred, and Golden less, and Granny average. Also this sample, this special sample, is very close to the intersection in the score plot, so it's quite an average sample. and that's the sample 7, that is friends and granny. Also, I can look at the loading plot and see that all the variables that are circled, they are the ones that are significant. There is a stability test that is performed, and they perform like they are stable. So here we have almost all the levels that are significant except Portugal. So here I can also make another grouping. I can group by countries, so by origin, and I can see that there is a gradient in each of the cluster. So we have a gradient with Spain, Portugal, France, this way. So then some other result is that in this model we need only 2 factors, and that's the result that we get when we predict the preference. We will get a very good result actually. We get an R square of 0.97, so that's the correlation coefficient square, which is very close and very close to 1. And we get an error in validation of 0.32. So when you predict between something from 4 to 10, it's quite a low error. It's less than 5%. So very good result. We have some more plots that might be important to see. So we have the weighted regression coefficient that tells you what are the effects that are the most important. So here we find that GALA is the most important because its B-weighted coefficient is the highest. So from this we can see that the type of apple is more important than the origin. Well, that's what we got from the normal DoE method, but it's good to get it confirmed this way too. Also we see that the one that has the least effect is Portugal, and that's what we saw as well in the summary table. So that is good. And a plot that look like that is very important because it gives you p-value that are kind of similar to p-value you will get in an ANOVA analysis. Is this one, PLS ANOVA p-values? And you have 3 limits. You have 5%, 10%, and 20%. So everything that is below the 5%, they are really significant, and the rest is less significant. So here, Portugal is not significant. Well, the reason for that is that basically in the analysis, when we do that, if it's not from Spain and it's not from France, it has to be from Portugal. So you may expect that some variable doesn't look significant because the information is already contained in other variables. So here, basically, everything is significant. So if I conclude on the analysis, we have 2 options for the analysis. We have PLS and classical results, and we have some new tables and new results that can help you to have a good diagnostic of your result. And we have plenty of new polls that I tailorize for each type of DoE module. So now I will make you a little demo. I have to launch the software. So I will create a new DoE. So I go to Insert and then Create Design. So here, test 1, and maybe I want to do a screening with interaction. Here I can type some information, and then I can go to the second table. So define variable, I click on Add, and here maybe I define one variable, this concentration. It's a design variable, there is no constraint, it's continuous, and it varies from 100 and 800. Then I add a second one, or maybe a ratio between 2 constituents, and that will be 0.4 to 0.6. The third one will be the time, and 20 to 80 minutes. And the last one will be the temperature, from 80 to 100. Then I can add some responses. I did not set it as a response, so I can set it as response this way. And the name did not. Okay. No, I have this one too. Response. Okay, so I have all the variable I want to define. Then I could choose the design, and I can select extensive analysis of design variable, and then it's a full factorial. Then I go to design detail, and maybe I realize that I can do another experiment that will give me less experiment to perform, so I can just select it, and here I have to perform 8 experiments. And this is my confounding pattern. So here I see that all the interaction with 2 variables are confounded together. But if it's good enough, maybe I will just take that. I can also show it with names, so I can see better what those interactions are and how they are confounded together. For the additional experiment, by default I have 3, so I will just keep that. And here we can randomize, so I randomize. And maybe I decide that I don't want to randomize the temperature. So I just change randomize temperature. And the temperature, which is the last variable, as you see, they should be all cluster by levels. Then summary. So here I could try to change some value to see if I have good power enough. And already, because we have 8 experiments, if we have a signal ratio value of 2, we will get a power that is good enough. And in the end I can just finish and import things. So here we have those 2 tables that one is the response and the other is the design. As you see, there has been some clustering. So we have one row set or sample set that contain all the samples, one that just contains the center sample, and so on. And for the column, we have the main effect, and then we have the interaction. So for the response, I will just copy-paste some data from Excel. And now I can run, so what I can show you as well is that here we are in standard order, but maybe you want to randomize it. So you want to have it in randomized order. So here you can just go to edit and then sort ascending. It just put the experiment in the randomized order. So you deal with it like that. So let's go to analysis. So tasks and then analyze, and the last option here is analyze design matrix. So you take this one, and here we take the classical method. Then we have to enter the model input. So we have the design table. Here we have main effect plus interaction, and here for the responses we have the response table. So we can just click on OK. And we can click yes to see the results. So on the top corner here we have the ANOVA table, where we can see that the model is valid, and we have only 2 effects really that are significant, so A and B. C and D doesn't look like they are significant, and the most significant effect, but still not significant, is the interaction between AB, or that is also confused with CD. But as we have CD not significant, the most likely is that AB is more important. Then we have to visualize the effect. So here we have the value of concentration, which is the A variable, low, center, and high. Maybe here, as you see, it's not such a linear decrease, so maybe there is some other things to look into. But for B, it's quite linear, so it's nice. We can also, there is plenty of other results. Here we have for the effect summary. So we see that for viscosity, A and B are the ones that are significant. And you also have the response surface here, where you have a response surface generator. So basically here we have A and B that are displayed, and then the C and D value are not displayed, but you can change the value between 20 and 80. So for example, here I can place myself at 20 and here at 100, because that's the maximum values. And I can click on generate surface and it will change the surface. Same thing, I can change the response I'm looking at. So this way I can interactively modify this plot. Then maybe I want to extend this design and work on the A and B variable. So I go to tools and then modify extend design. And here I have only one design, so it's very easy to select it. And I can select to do now an optimization. As you see, it says that I'm modifying it, well, 7 minutes after I started to create it. So then I can go to define variable. Maybe here I suppress or delete B and C, C and D, and I only keep A and B. I could also modify the value if I needed to, and but I will not do that. I will just select the default value for the central composite design. True experiment for center is enough. Can just re-randomize. Summary, design table. I import it in standard order. It's easier to copy paste the result. And I will copy paste, or I will import. I will do an import. Import data from Excel. Optimization, and here I want to select this part of the table and import it. Then I can do a copy paste and I place it into the responses. And now I can analyze again. Task, analyze, analyze design matrix, model input. Here you see I have the quadratic effect. I could use cubic, but they will be, if it's only 2 variables, it's not very important to do that. So here we can just click on OK. And here we get a nice response surface. And here in the ANOVA table, we have, in addition for the sources of variation, AB, A square, and B square, and the lack of it. So more information. So I think that's what I wanted to show you for the demonstration. So I can now finish the presentation. So as general conclusion, there is 13 available types of design, because there is basically 6 different types, but then in each type you have several options. And then we have 2 options for the analysis. So we have PLS and the classical method. And for each method we have some tailorized plots by design type. So the benefit of this DoE module is that it's very easy to use. So it has an intuitive workflow and guidance for design creation and modification. Also, you can check the power of your design beforehand, so you don't have to realize that it was not good enough in the end. And also, it's very easy to interpret because you have a color-coded response results, so it helps you in your diagnostic. This webinar has been recorded, so you will be able to find it under camo.com and then /training/webinar seminar. So it will be in the archived webinar, so you can search for it. Also, we have DoE web training coming up the 20th of July. So if you want to sign up for this, you can also find information on our website. And now I will take questions if you have some about this presentation.